Hello everyone, welcome to the first video in my Intro to Real Analysis series. This is our week 1 video. In this video we're going to talk about what analysis is and why people study it. We're going to do some set theory review, functions review, and then we're going to talk about the common proof techniques that people use, because in this class, if you don't know already, we're going to be doing proofs for almost every problem. So we're going to, I'm going to make sure that you guys have a solid foundation with that first before we start proving results in analysis. Okay, so what is real analysis? Well, in short, it's just the study of real valued functions. So when I say real valued, I mean the outputs of the function are real numbers. And same thing with sequences and series. So we're going to be looking at everything that, well, not everything, but we're going to take the things that you learned in Calc 1, 2, and 3, and we're going to prove some of these results rigorously. And so what do we care about in analysis? Well, in calculus, we care about limits, we care about convergence, distance, right? In general, we care about distance. So we're going to be proving lots of results about how close things are to each other. So here's some questions you could ask in an analysis course, and we're going to be answering all of these questions. So in calculus, you found limits, right? That's probably the first thing you did in Calc 1 is you evaluated piecewise functions, and you looked at different limits for various x values, independent variables. But the question we can ask next is, well, how can we prove that that is actually the limit? We know how to do it visually. We know how to do it with functions, polynomials in particular. We just input the whatever x is approaching into our polynomial, and then we get an output, and that's our limit. But how can we prove this rigorously? Okay. Also, we can ask, what does it mean for a sequence to converge to 3? So what does that mean for a sequence to get really, really close to 3? What does that mean rigorously? And so that is what we're going to be doing in this class, just focusing on questions about distance and closeness. Okay, so why did people start studying analysis to begin with? Well, in the 5th century BC, Zeno posed a list of paradoxes to show people how strange infinity behaves. And so one of my favorite versions of the paradox is the clapping hands version. People usually talk about the one with the tortoise and the hare, and actually I think that's the one in the textbook, but I really like this one better. So imagine that, you're about to clap your hands are 2 feet apart, but before you clap your hands, when they're traveling towards each other, they have to go a foot, right? They have to get close, they have to half their distance, in other words. But then they have to half their distance again, right? Before they meet, they have to half to get to a foot apart, and then they have to half again to get to half a foot apart, and then et cetera, a fourth of a foot, right? And this process theoretically can go on forever and ever and ever. But clearly we know that you can clap your hands and it's not going to take an infinite amount of time for you to do it. But these conflicting ideas between mathematics and physical reality is really what sparked a lot of interest with analysis and with calculus. So, how can we treat these series and these sequences in a rigorous way so that they make sense to us? Okay, so how can we handle the infinite is really the motivation before calculus was even discovered. How can we deal with infinity? So here's a short little timeline. I'm not going to harp on this too much, but calculus was developed by Leibniz and Newton in the 1600s and 1665, and I'm not sure that this is the exact date, but that's roughly when they developed calculus separately. And the reason calculus was being studied at this time is to answer questions about physical phenomena, in particular planetary motion, projectile motion, and actually, funny enough, Kepler, astronomer, mathematician, was wondering about calculating the amount of wine left in his wine glasses of different shapes. And so this goes this is regarding volumes of revolution. That's what we think of this question as, a volume problem. But yeah, so they had lots of questions about the physical nature of our world, and so calculus was developed to answer this. In the 18th century, Euler introduces the notion of mathematical function, and it wasn't until the 19th century, in 1816, that Bolzano introduced the modern definition of continuity that we use in analysis. So we're going to be proving that a function is continuous at a point rigorously, and that was developed by Bolzano in 1816. And when things started really getting serious with analysis was in 1821 with Cauchy. So Cauchy saw a lot of holes in Leibniz and Newton's work. And so there's this thing called the generality of algebra. And so basically what that means is you're handling infinite quantities like you would finite quantities, and that results in contradictions, problems, right? So for example, look at this sum, this infinite sum. What is it? Well, it depends on how you interpret it, right? So you could say, oh, well, it's 0, right? If you group it like this, 1 minus 1 plus 1 minus 1, etc., is equal to 0, right? You could say that. But what if you grouped it a little bit differently and you said 1 plus minus 1 plus 1 minus 1 plus 1, etc., and so now we have 0 plus 0, but here's the 1 in the front. So how do we group this? And of course we know the answer to these questions now. But there were, and I'm not familiar with all of the different contradictions, but that was the idea. So make calculus rigorous, and yeah, and so that's what Cauchy did. That's who really started analysis, was Cauchy. Okay, so now we're going to our review. Before we start getting into the weeds of the actual analysis part, I want to do some review with you to make sure we understand the basics. Okay, so the first thing we're going to talk about is what is a set. Okay, so a set is just an unordered collection of distinct objects which are called elements. So I have some examples of sets for you. This is set A, curly brackets, right, are surrounding the elements in the set. So in our set A, we have 1, 3, 9, and 6. Cool. But guess what? This is the same as this set because we don't care that elements are repeating in a set. It's the same thing, right? The set is unordered, and we only count the 3 once. You don't have to have numbers in your set. You could have something stupid like this. B is equal to blue heart smiley face. That's a perfectly valid set. Anything you want you can have in your set. You can have sets of sets. If you wanted to get crazy, you could put A, B, maybe a set of a set of a set. I don't know. But anyway, that's the definition. All right. Here's our set C, -2, 0, 2, 4, 6. What are these? These are the even integers, right? And we'll denote this as 2z. This is even integers. Hopefully this is all looking familiar. Okay, so here's some special sets that we're really going to talk about a lot this semester. All right, the first one I just alluded to is the integers. So your positive and your negative whole numbers, including zeros. That's a set of integers, and we do this little z for that. History for that, I don't know. Maybe someone else knows. Anyway, okay. Z plus, positive integers, okay? Excluding 0, so just 1, 2, 3, 4. Z minus is the negative integers. And this Q, this represents the rational numbers. So basically all of your fractions, okay? So you have an integer over an integer. That's what this means, integer over an integer. And this guy means such that. So A over B such that, the colon. A and B are in the integers, and B is not equal to 0. Okay? So, we can never divide by 0. That's the big no-no. We don't do that. And R, this little funny-looking R, is all real numbers. Okay, so let's talk about some terminology. You're going to get to a point in your math career, maybe, when everything you write down looks like something that an alien sent from outer space, and your family and friends will question you and make sure you're okay. But anyway, so this is, I'm showing you this alien stuff. Maybe you already know this, I'm not sure. But anyway. All right. So this X, this little E thing means in, okay? So, or contained in. X is contained in S, means X is in the set S. Okay? X is in S. All right, so for instance, we could say all of these things. We could say 9 is in A, right? Here's A. Here's 9. 9 is definitely in A. Okay, 2 is in Z plus. Yes, 2 is a positive integer, indeed. What do you think this means? Not in, right? With the slash. Okay, so this means 3 is not in the negative integers. And 4 over 5 is in the rationals. Okay. Next thing is this null set. This is the empty set. Okay, so this is the set with no elements. The empty set is contained in every set. Next bit of notation is this. A subset B. Well, whatever. Okay, this means A is contained in B. It's completely contained in B. And what is this that I wrote here? Oh, IE. I was like, what? IE. A is a subset of B. Or is it EG? Anyway. Another way to express this idea that the set A is completely contained in the set B is the following. If X is in B, for every X in A is contained in B. Okay, so if X is in B, for every X in A, if X is also, maybe I'm going to write this differently. That's not a great way to write this. Let's write it again. So, if for all X in A, X is also in B, then A is completely contained in B. So if every element X is in A implies that that X is also in B, then we know that the set A must completely be contained in B. Okay? So that's what that means. All right? Let's go to the next one. Okay, so let's talk about some subset examples here. So remember, this means is contained in. Okay, that's what that means. So 1, 4, and 25 is contained in this set. Okay, why? Well, n can be any integer. This is an infinite set, so we let n run as it will with this rule. We say, okay, well, n is going to be If it's any integer, we could have, -2 squared and so forth, -1 squared, blah, 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 0 squared, whatever, 1 squared, et cetera, et cetera. So that's the infinite set here. 1 is in there because 1 squared and -1 are 1. 4 is in there because 2 squared is in there, right? N equals 2 gives us 4. And 25, if we let n equal 5, 5 squared is 25. So that guy's in the set too. All right. The integers are completely contained in the rationals. Okay, so try to convince yourself that that is true. Every integer can be represented as a fraction, right? So if you have an integer z in z is equal to z over 1, right? So remember our definition for the rationals. Q means that a over b are going to be integers, and 1 is, of course, an integer. So, yeah, z is completely contained in Q. All right, we can write the containment either way. I mean, it's like the inequality signs, right? So, like, you can read it like this. You can say, this set, purple, contains this set, if you read from left to right. Or, if you read from right to left, you can say, this guy is contained in this guy, right? Okay, so convince yourself that this is true. So why does this set contain these elements? What's the reason? Well, the reason is that every element in my set is of the form 3 times x, where x is a real number. Any real number, okay? So this is an, I don't know if you guys talked about this in discrete math, but this is an uncountably infinite set, okay? Because the real numbers are uncountably infinite. Maybe we'll get into that more later, but the whole thing is that x can be any real number. It can be pi, it can be root 2, it can be whatever. So, yeah. So convince yourself that 3 root 2 is in here when I let x equal root 2. 12 is in there, letting x equal 4, yada, yada, yada. Okay? So create the set with a rule. Okay, so this is just some practice. How can we make a set with a rule out of this? Well, I mean, there's a couple different ways, I guess, you can look at this, but notice these are just the even integers. So you can say, my set x is equal to, we could say, 2x, such that x is in z. Right? That's one way to represent my set with a rule. What about this one? Oh, look, I left something out here. What was that? Well, what's the pattern? Well, let's see. 1 over 3 to the first, 1 over 3 squared, 1 over 3 cubed, 1 over 3 to the fourth, etc. Okay. So this is going to be what? 1 over 3 to the x, such that x is in z. Well, no, because it looks like the set terminates here. It's not getting any bigger than 1/3. But if it goes, if it gets smaller and smaller in the other direction, we can let x be any positive integer, right? So x is going to be in z positive. Okay, so that's my set. Let's see where we're at on time. Okay, good. Okay, moving forward. I'm hoping this is all a review, but we'll see. Okay, here's some other stuff. Intersection. A intersect B. If you use LaTeX, A cap B. We'll talk more about the LaTeX stuff in the Canvas shell, but anywho, the intersection are the elements that are in both sets. Okay, so the intersection of A and B are going to be, let's read it, the elements such that the element is in A and the element is in B. I almost said the elephant is in B. No, the element. Okay, so that's what this intersection represents. Things that are both in the set A and the set B. All right, the union means that it's going to be the elements that are either in A or B, or possibly both. Okay, so what I mean is including the intersection when I say both. So this green shaded region is going to be A union B. So everything in A or everything in B. Okay. This guy in purple is set the complement, set minus. Well, I shouldn't say the complement. Scratch that. Just set minus. You can read it as A without B. Okay, that's what you should read it as. A without B. And so these are the elements in A. And let's see, X is in A and X is not in B. Yeah. Okay, so the elements that are in A but not in B. Okay, so we wouldn't include this piece because even though this red piece is in A, they're also in B. So we don't want that. We want A without B. So that would just be the purple piece. Okay. A and B are disjoint if their intersection is empty. So what that means is that they literally just, it's exactly what you think. They don't cross anywhere. They're disjoint. Their intersection is empty. They don't have any elements in common. Okay, let's see what we have next. All right, so if we have a finite number of sets, A1 through AN, who knows what N is? But the point is that it's a finite number of sets. Then the finite union, okay, we call this the finite union from 1 to n of AI is just going to be the union of each of these sets. A1 union A2 all the way up to AN. And same thing for the intersection, the finite intersection is going to be A1 intersect A2, yada yada, all the way to AN. We're also, in this class, we're also going to talk about infinite unions and intersections. So if you have an infinite list of sets, specifically with this one, countably infinite, you can still take the union, but at some point you're going to have to put the union ... to say that this union goes on forever. So this is the start of the union, I equals 1. It's like your index here is the I. So you start at I equals 1, go all the way up to infinity, which of course you can't get to. So we will talk about quite a bit in this class. The cardinality, this is another term that you've probably heard, hopefully. But anyway, the cardinality of a set is just the number of elements in the set. So you can have a finite cardinality or you can have an infinite cardinality. And this is what I said earlier that I didn't mean to say. The complement of A is going to be everything that's not in A. So this is different from B without A, because this time we're looking at the ambient space. So like the stuff that's outside of A and B is also in the complement. So A complement is going to be everything outside of A, including the ambient space, which I'm shading in red. Yeah. Since this is real analysis, we're thinking of our ambient space typically as the real numbers or real vectors. But yeah, that's the idea here with these. Okay, so check your understanding. Let's just do it. Yeah, you know, I encourage you guys to pause these videos and try these out before I work them out. See if you get them right. So let's see. Okay, so A intersect B is our first one. So what elements are in both A and B? Well, it's going to be 1 and 3, right? Or in both A and B. So that's our answer. So things in A or B. Okay, so that includes everything in A and everything in B. And we don't have to write elements more than once. So A or B. So that's going to be 1, 2, 3. We don't have to write that 1 again. Or the 3 again. 6, 7. Okay. A without B. So imagine that I have A right here and I want to get rid of stuff that's in B. Well, the stuff that's in B is 1 and 3. So if I get rid of that, then A without B is just 2. B without A, well, we're going to get rid of the 1 and 3 because those are in A. So it's just going to be 6, 7. Okay, cardinality of A, count the elements. 1, 2, 3. That's 3. Cardinality of B, 1, 2, 3, 4. Beautiful. Okay. All right, next example. A intersect B. So what's in both the rationals and the integers? Well, remember I said earlier that the integers are a subset of the rationals, right? So if you drew a little picture, here's your Q, here's Z, 1, 2, 3, 4, blah, 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 blah. And then here's your other stuff, like 1 over 2, 3 over 4, I don't know, whatever. All these other rational numbers. So anyway, what's the intersection? Well, where do they intersect? In Z, right? Now, what about A union B? So what's Z union Q? Okay, what's in both Q and Z? Well, all we have to do is just include this outer ring as well as the red piece, and that's our union. So it's simply Q. It's our union. A without B, so that's going to be Q without Z. Q without Z. If we take away Z here, what do we get? Well, we get the following. It's not really I don't know. It's like the obvious thing that you would think, right? It's P over Q, so that Q and P is in the integers, and Q does not divide P, right? Because if Q divided P, we would have something like this. So this is the bottom. Q divides 8. That's going to be 2. I don't know, 16, 32. Same thing here. So Q divides P, so that's 2. And those are integers. So yeah, Q can't divide P is how we can exclude our integers. So the cardinality of A, how many rational numbers are there? Well, infinitely many. How many rationals? Infinitely many. And how many integers? Also infinite. That's the cardinality. Okay, let's do another example here, a little bit, more abstract, I guess. So here all of our sets are of the form A sub n equals, we call this an open interval with the parentheses in the end. If it were brackets, we'd call it a closed interval, from -1 over n to 1 over n. So we're not including those endpoints, if you remember that from college algebra or whatever, whenever you learn that. So we can represent these sets on a number line. We're trying to take the intersection and the unions of these infinite, the infinite intersection, the infinite union of these sets of the form -1 over n to 1 over n. So let's just draw a little sketch here. Okay, so for our intersection, well, we start at n equals 1. So when n equals 1, we get -1 to 1. When n equals 2, we get -0.5 to 0.5, and so forth. This process goes on forever. So let's represent this on the number line. Here's -1 to 1. Here's -0.5 to a half, negative a third to a third, etc. Okay, so this process is going on forever. And the question is, what do all of these sets have in common? Right? What's the common element in all of these sets? And, well, the answer is going to be 0, because we're never, no matter how large n gets, we're never going to exclude 0 in any of our sets. So our 0 is going to be right here. And the idea here, I mean, this is going to, come up endlessly in analysis, is we can make n as large as we want. So if n was, I don't know, like a trillion or something, okay, it'd be this tiny, tiny, tiny little neighborhood around 0, but it's still going to include 0. Okay, that's the idea here. So our intersection is just 0. Okay, and we're going to make this idea of closeness rigorous later on, so that we can prove these things. But for now, it's just about getting the intuition, I think. Okay, so what's the union of all of these sets? Well, if we union all the sets, what is included in all of these things, right? If we're looking at all of the elements in all of these sets, well, what's included is simply -1 to 1, right? Because through this iterative process, our neighborhoods are getting smaller. They're shrinking. They're never going outside this way. You know what I mean? So our union is going to be all of these elements inside -1 to 1. Of course, we're not including those either. Okay, so that's our union. All right, let's see what is next on the agenda. All right, here's some definitions. You've probably seen them before. Given a pair of sets A and B, so we suppose that each element X in A is associated in some way to another element of B, which we denote f of x, this function notation that you've all seen before. Then f is said to be a function from A to B. This is a little bit sloppy, I admit. It's technically what we call a relation, because functions have, there's like an issue, right? You can't have something in your input going to two things in your output. Remember the vertical line test. But, we're not going to be super picky about that for now. Okay, so we can think of a function as going from A to B. So from our input set A to our output set B, or sometimes we call B the target space. Okay, A is called A the domain, and B is called the codomain of F, and the stuff that gets hit by the map is called the range. Okay, so the set f of x such that x is in A is called the range of F. So any possible output values you can get from applying this function to A is the range. Okay. So suppose B prime is contained in B. We defined the inverse image, okay, as being A in A such that f of A is in B prime. Okay, so if we were to draw these things, let's go ahead and just do a little sketch. So here's A, here is B. Inverse image also might be a problematic term to some people, because you may have a non-invertible function, but let's worry about the details later and just get the intuition for now. Okay, so here is A and B. Let's say that B prime is contained in B. And so this F, I say inverse, but yeah. So F inverse, the inverse image of B prime is going to be all A's and A's such that F of A is in B prime. So, suppose we have, this is all of the stuff that gets mapped into B prime. Okay, so this is my inverse image, and so this is F going this way. Okay, so yeah, so it's going to be this subset right here is what this is. Okay, just this piece, the stuff that gets mapped into B prime under the map F. Okay, so a function f from a to b is called injective or one-to-one. If f of a equals f of b implies that a equals b. Basically what this means is that you can't have two different things in your input space going to the same output. So you can't have, for instance, 6 and 2 both going to 3. Okay, that's why they call it one-to-one, because each element gets sent to a unique element in the codomain. Okay, so this is an example of an injective function. So this is our f, and this is our domain and our codomain. And yeah, you can see that no two elements go to the same thing. Okay. On the contrary, this picture right here, this is not injective because the element 1 and 2 both go to 4, okay? Not one-to-one. Let's look at an example of a function we know and love. Linear functions, or a linear function. Is going to be this function f of x equals 3x, and we're going from R to R, and we're going to prove that. Let me make sure I do some of these proofs. I think we do. Yeah. Okay, good. Yeah, we're going to prove injective and surjective, but yeah, this linear function is one-to-one. Another way you can think of it is that it passes what they say is the horizontal line test. So no different outputs go to the same, no different inputs go to the same output. Okay, so like if you were to draw this linear function, f of x equals 3x, it passes the horizontal line test. So if you draw a horizontal line anywhere, it's only going to hit it once. Whereas with something like this, not injective, could have something like this. We all know and love this guy, right? F of x equals x squared, where we're looking at f from R to R. No, this is not injective because look, it fails the horizontal line test. It passes these two guys. Okay, so what could these be? What could these points be that I just randomly drew here? Well, think of the function y equals x squared. What are two different inputs that have the same output? Well, you have -1 and 1. You have -2 and 2 produce the same output, right? -1 squared equals 1 squared equals 1. Blah, 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 blah. And so forth, right? So yeah, not injective. Okay, we can also talk about a function being surjective, or onto is another word that people like to use. If for every b in your target space, there exists some a in your domain such that f of a is equal to b. Okay, so for example, this guy is surjective because everything gets hit by something in A. Everything gets hit by something in A. Whereas this guy is not, because this guy is not getting hit. Okay, not surjective. Everybody has to get hit. A function is bijective. Okay, think by two if it's both injective and surjective. Okay, we're going to talk about that a little bit more. All right, now I want to review these proof techniques because it's very important that you know how to prove stuff. Really, really, really important in this class because that's pretty much all we're going to be doing. Okay. So, the first technique I want to talk about is that of direct proof. So, you're trying to prove a statement. You want to prove that some statement A implies some statement B, okay? And we denote this with A arrow B to say A implies B. And we want to start with the known facts or axioms about A and deduce a result about B, okay? And that sounds so general, and it is. And honestly, like, this stuff takes so much practice, okay? So if you find yourself with the homeworks and you're like, oh my gosh, I am garbage at proofs, just know that you're not alone, and everyone starts with garbage at proofs. It just takes a lot of practice, and that's the honest truth, okay? So if it doesn't, if it's weird and it doesn't make sense at first, it's okay. Just know that it's okay. All right. So here we go. So I'm going to try to make this, so, what is difficult about writing proofs is that sometimes, not really with these that I'm going to show you, but if you continue on to grad school, PhD, math, whatever, sometimes it's like not obvious where to start at all. And it's kind of a creative process a little bit because you're like, okay, like, there's no formula for how to do it really. I don't know, but let's try to do this as algorithmic as we can possibly do it. So here's the first proof we're going to look at. If n is even, then n squared is even, okay? So first of all, what's A and B? We're trying to show that A implies B, okay? So A is going to be what? What statement? N is even, right? We want to show that n being even implies that n squared is even. Okay, so we want to use everything we know about A, and we want to deduce from that stuff about B. Okay, so what does it mean for n to be even? What does that mean? Well, that means that n is going to be equal to, I don't know, 2, 4, 6, 8, negative 10, negative 20. How can we generalize that? We can say n is equal to, people like to use k. I don't know why, but yeah. N is equal to 2k. Oh, shoot. Okay, n is equal to 2k. Actually, let's be elegant about this. Let's just say suppose. Okay, so this is the beginning of our proof. All right, so we're going to suppose n is equal to 2k. That's the premise. We're trying to show that A, capital A, meaning n is equal to an even integer, implies B. And k can be any integer, right? So that's what does it mean to be an even integer? It means the statement right here, okay? If n is an even integer, is equal to 2 times some integer, right? That's what that means. Okay, so that's where we're starting. Okay, so suppose this, and now we're going to say, consider n squared, right? We're trying to use what we know about n to deduce something about n squared. So what is n squared? Well, we know what n is, so we simply say, okay, n squared is then n squared, right? And what is this going to be? This is going to be 4k squared. Okay, we're trying to show that it's even. And what does it mean to be even? 2 times k, where k is an integer. So I can write this to show evenness as 2 times 2k squared. Okay? Right? The end goal is to show that it can be written as 2k. Okay? So that's the idea. So yeah, so what else do we have to say? We have to say that this guy is an integer, right? Let's see. Maybe I'll just draw a line right here. Since 2k squared is an integer, this shows, and I'm going to write all of this out at first, but not forever, just to give you the intuition. This shows n squared is even. Right? All right. Let's do another one. Okay. So prove that if A is contained in B, then A is contained in the intersection of A and B. So to do these kind of proofs with sets, you want to use the elements in the set. All right, so first of all, what's our premise and what's our conclusion? Well, our premise, and this is confusing because I used A here, but whatever. Too late now. Our premise is going to be A is contained in B. So this is what we're assuming. And we want to show that this implies that A is contained in A intersect B. Okay, so this is our goal to show. And you know what? When you're first doing this stuff, you should really write all of this out. And I'm going to be better about this starting now. So let's go ahead and do this the old-fashioned way until we really get a feel for this. Okay, so to show, I like to write that whenever I'm trying to prove stuff. A is contained in A intersect B. And we know that A is contained in B. So I like to just kind of put this off to the side. So we want to start, since this is a set proof, we want to start with the elements, okay? And I always like to draw pictures, okay? Don't be embarrassed to draw pictures. It helps, I think. So this is the situation, all right? We know that A is contained in B. Here it is in the picture. Beautiful. A is contained in B. We want to show that A is contained in the intersection of A and B, all right? So what do we know, all right? So we know, maybe I should say proof. And I'm just going to write everything out. So we know that since A is contained in B, whenever X is in A, this implies, that's that arrow, that X is in B. Okay, that's what we know. All right, now we want to just say, okay, take an arbitrary element of A and show that it's contained in the intersection of A and B. So, in other words, it's in A and B. So, take an element, A in A, then A is in A. I don't have to write that again. But here's what we know from our assumption. Whenever any element is in A, it's automatically in B because it's a subset. A is a subset of B. So take an element A in A. Since A is contained in B, this implies that A is contained in B. What are we trying to show? We're trying to show that this little a is in both A and B. Okay? We've already said take an element A in A. It's already in A. But now it's in B as well because A is contained in B. All right, so take an element A in A. That's done. Since A is contained in B, A is in B. Therefore, A is in A and A is in B. And thus, or therefore, A is in the intersection of A and B, just by definition. Okay, that's just our definition of intersection. And so the proof is done. And we can celebrate and put this box, or if you're really pretentious, you can put QED. But I don't put that. So anyway, you can put QED if you want. I won't judge you. Okay, let's carry on. All right, so here we go. Let's look at this one. All right, so here's another one. So again, anytime you're doing these set proofs, start from the elements. Okay, start from the elements in your set. So try pausing the video, see if you can come up with something here. All right, we want to prove that A union the empty set is equal to A. All right, so whenever we're trying to show set equality, we want to show the following. I'm going to write this as a note. When showing set equality, let's just say, I'm just going to say, let's say a set S equals a set T. When we're trying to show this, we want to show first that S is contained in T. We want to show this. And then second, we want to show that T is contained in S. If we show both of these things, then the sets have to be equal. Okay, so that's a strategy that's very important that you're going to use all the time. All right, so the first thing we're going to do is we're not going to be sloppy, and we're going to write proof. And the first thing we want to show is A union the empty set is contained in A. Okay, we're trying to show set. That's a set. We're trying to show set equality, so we want to show both containments. All right, so how are we going to show this? Well, remember, we have to start... we want to show that an element in here has to be in here. Okay, if an element's in here, then it must be in here. That's what we need to show. So suppose an element A is in A union the empty set. Then you say, what does it mean to be in the union? It means that that element's in either A or empty set. Okay, so let's write that. Then either that element, either little a is going to be in capital A or little a is going to be in the empty set. But, of course, by definition, A cannot be in the empty set because it's empty. Okay? So A is in A. Someone's cackling in the background. So A is in A. All right? And there we have that first direction. Therefore, since we've deduced that this thing that was in here ends up in here, we've proved this containment. A union empty is contained in A. Yay, rejoice. Now we do the other containment. We want to show that A is contained in A union empty set. And, you know, you're like, oh, this is, I don't know, maybe you're thinking this is obvious or something, but it helps to just just do it. Just practice these things. And I'm serious, like, when you get to a point where it gets weird and it gets hard, I'm serious, guys, it's a very normal thing, and you just have to push through it. The only way it gets better is through practice. All right, so here's the next one. A is contained in A union empty. So what do? We need to show that something here ends up here. Okay, so we're going to say let little a. Okay, so this is a different part of the proof, so we're just starting over again. So let a be an a. That's where we're starting. We want to show that it's in here. Okay. Well, that's, I mean, I don't want to say, I try to avoid the word trivial, but what it means for a union empty set, what does that mean? Well, it just, so then a is going to be in either a or any set you want. It doesn't have to be empty, but, you know, if a is in capital A, it's going to be in the union of a and anything else. So, you know, trivial. Done. Okay. Okay, let's look at this next one. So again, I encourage you to pause the video, see what you can come up with here. So we want to show, oh, I guess I wrote it twice. We want to show that these two sets equal each other. Okay, so set equality means that we want to do both inclusions. So first, we want to show that A union B intersects C is contained in A union B intersect A union C. All right, so we want to start with something here, okay? So, you know, I've kind of used a little bit too much, so I'm going to just choose a different letter, X. So I'm going to say proof. That's what we do here. We write everything in order and neatly. Okay, so proof, we're going to let an element X be in A union B intersect C. Okay, and we have to say, what does that mean? Okay, so we're letting an element be here, and we want to show that it ends up in here somehow. What does that mean? Well, what does union mean? We want to look at this outer thing, right? We want to say what this means. What does it mean to be in the union of two sets? Well, it means that either, maybe I should say then X is either an A, right? That's what union means, either an A, or it's going to be in this set B intersects C. Okay, so if X is an A, we'll start with that case first. Well, you know, we're trying to show that this element, in either case, if it's in A or if it's in B intersects C, ends up here, okay? That's the goal, okay? So always keep the goal in mind. So if X is in A, does that mean that X is in this set? Well, we can say that certainly if X is in A, then X is in the union of A and B, certainly. Also, since X is in A, it's in A union C, right? And so by definition, since it's both in this and in this, it's in the intersection, okay? Thus, X is in the intersection. Oops. Cool. All right, so that case is taken care of if X was in A. But now let's see what happens when X is in B intersects C. Now, if X, remember, okay, always, you know, check yourself to make sure you're understanding the logical flow here. I'm saying at first that the element was in the union. And what does an element being in the union mean? It means it's either in this set or this set that it's being unioned with. I already took care of the case when it was in the first set, A. Now I'm taking care of the case where it's in the second set, B intersects C. Okay? So Now, if X is in B intersect C, what does that mean? Well, that means then X is in both B and C. X is in B and X is in C. That's what that means. Remember the end goal, okay? Remember the end goal. We're trying to show that X is in the intersection of these sets. So can we say something in terms of these sets if we know X is in B and X is in C? Well, yeah, actually we can. Because X is in B, guess what? It's in the union of A and B, okay? Because X is in B, it's in the union. So let's write that. So because X is in B, this means that X is in, maybe I should do the implies. This means that X is in A union B. And because X is in C, this means that X, well, what else did we need? We needed that piece as well. X is in the union of A and C. Okay, so what were we trying to prove? We were trying to prove that X is in the intersection in this second case. So we've shown that X is in A union B and X is in A union C, which is precisely what it means to be in the intersection. Thus, X is in A union B intersect A union C. Cool. All right. So we're done. We have taken care of this first containment. A union blah, blah, blah is contained in A union B intersect A union C. Now we need to do the other containment to show equality. Okay, so let's do the other direction of containment. So the first thing we need to show, or the second thing we need to show rather, is A union B intersect A union C is going to be contained in A union B intersect C. Okay, so the idea is the same. We're going to start with something over on this side, and we're going to show that it ends up over on this side. Okay, so we're going to let X, our element X, be in the set A union B intersect with A union C. And we want to say, what does that mean? Well, by definition of these sets being intersected, that means that X is going to be in A union B and X is going to be in A union C. Then X is in A union B and, right, intersection definition, X is going to be in A union C. Okay, and we want to show that this implies this end goal, that X is actually in A union B intersects C. All right, so maybe we should just write out the possibilities and show that any way you hack it, you end up here. Okay, so since X is in A union B and X is in A union C, we can have the following possibilities, right? Both of these things are going to be true. So X being in A union B means that X could be in A or B, right? So, and also X is in A union C. All right, so both of these things are true. So the first possibility that we could have, I always want to take this as case by case if it's not clear what to do. The first possibility is that X is just in A, right? X is in the union of A and B, so it could just be an A in this case. And also, it's in the union of A and C, so it could just be an A and not in C, right? Remember that union sign means or. X is in A or B, and X is in A or C. So the first possibility is just that X is in A. The second possibility, we could have that X is in A and X is in B, right? But maybe X isn't in C. Maybe it's just an A, B, and yeah, an A. That's it. Maybe it's just an A or B. So that could happen. So X is in A and X is in B. That could be a possibility. What about a third possibility? It could be that this element is in all three of these sets. It could be in A, B, and C. Is that X is in A, B, and C. That's definitely a possibility. Or we could have X is in B and X is in C, right? We could have that possibility as well. So those are our possibilities. And the question is, do all of these possibilities end up here? Okay. What was the fourth? Okay, yeah, just B and C. It could be in B and C. So those are our possibilities. And I encourage you to draw some pictures if this isn't totally obvious. Draw some pictures. Okay, so possibility 1. If X is only an A, is it in this set? Well, yeah, because this set is A and all this other stuff. Okay, so anything in A and anything here is in that set. So, yes, that works here. The second one, X is in A, and X is in B, will automatically, if X is in A, it's in this whole set because it's an A union B intersects C. So that's true too. Same thing here. A's in it, bam. So if A isn't involved and your element is just in B and C, well, it's going to be in this set as well because this is A or this intersection. And being in B and C means that it's in this intersection. So it can be in either set, right? That's what that union means. It can be in either set. So this qualifies as well. And so we're done here. We've exhausted all possibilities for X being in this set right here. And we've concluded that X lands in this set right here. So therefore, X is in A union B intersects C. B intersects C. And we are done. So we have shown both containments. And thus, these little 3 dots mean thus, or therefore, it's true that equality holds because we've shown both containments. I'm just going to say equality instead of writing the whole equation. But that's how that goes. All right. So next kind of proof that you'll encounter is function proofs. Maybe you've seen this in discrete, but if we want to prove something is bijective, remember by definition we're trying to show it's injective and surjective. That's what bijective means. So to show f of x equals 3x plus 1 is injective and surjective. I encourage you to go back to your definitions because that's all we're using here is definitions and logic. Okay, definitions are very important. So first, injective. So how do we start the proof? We want to show that this function is injective. We want to show, what does the definition say? So injective means, this is just a reminder, whenever f of A equals f of B, this implies that A equals B. So we want to show with our situation that when this premise is true, this conclusion follows. Okay, so this is like our A our premise, and this is our conclusion B. Okay, we want to show that this follows. So to start this, I write proof. Okay, and the next thing I want to do is I want to start with my premise. Okay, the premise is that that this is true. We want to show that this being true implies this. Okay, so we want to show that f of a equals f of b implies that a equals b. So suppose f of a equals f of b. Okay. Now, what does that mean in our terms? Okay, we just plug in a into our function and b into our function. Then we have the following. We have f of a equals 3a plus 1, just plugging in a for x into our function. And I'm just writing it all out. Equals 3b plus 1. Therefore, since we supposed this, we set them equal to each other, right? So therefore 3a plus 1 equals 3b plus 1. And of course, we all know how to solve equations. Subtract 1, divide by 3, and this implies that a equals b. And that's perfect. That's what we were trying to show. Okay? Oh my gosh, was that thunder? Oh. Okay, so thus f is injective. Okay, so we've done that. Excellent. Also, yeah, we're working in the real number. I'm not going to go into that. I'm going to stop myself before I go crazy. Okay, so the next thing that we're going to show is now to show bijective means injective and surjective. So f is surjective. And what does that mean by definition? Well, that means that we want to show that there exists actually, let me say this. Show that for all b in R, right? Because that's our target space here. F is going from R to R. So everything in R, okay, so for all b in R, there exists an a in R such that f of a equals b. Okay? That's what it means to be surjective. Okay, so everything in our target space has something in our domain that corresponds with it. Okay. So here's the scratch work. Maybe. Yeah. Okay. Well, yeah, I'm going to do scratch work off to the side for this part. Just because we want to write everything kind of neatly when we finish our proof. Okay. So f of a equals b. Well, we for our scratch work, we can just say, okay, well, f of a is going to be 3a plus 1, and we want that to equal b, and we want to find the a that works, okay, the a that works for this given b. So solve for a, so we get 3a equals b minus 1, so a is equal to b minus 1 over 3. Okay, cool. So that's it, all right? So now back to the proof. So let b in R be given. Be given. And consider our a that we just found through our scratch work. A is equal to b minus 1 over 3. And of course this is in the real numbers. Well, then we have the following. We have f of a is just by what a is, f of b minus 1 over 3. And this is going to be equal to 3 times b minus 1 over 3 plus 1, just inputting this into our function. And when you simplify this out, you get b. Okay? So we have found an a such that f of a is equal to b, and therefore f is bijective, or surjective. And this implies, since it's injective and surjective, f is bijective. And then, again, QED if you're pretentious, box if you're not. Okay, so that's the end of our proof. All right, let's see what we have next. So we've been doing direct style proofs. The next kind of style that you'll learn to love is proof by contradiction. And so the logic here is that you assume that the statement that you want to prove is false and show that this leads to a contradiction in the premise. Okay? So the classic example of this is prove that the square root of 2 is irrational. And so how in the world do you do this? Well, the strategy is to assume that it's rational and derive a contradiction. So that's what we're going to do. So suppose, for the sake of contradiction, that it's actually rational. And let's see where things fall apart. Well, what does that mean? Okay, you want to say, okay, well, yeah, all right, I'm supposing it's rational, but what does that actually mean in math? So that means that the square root of 2, and we can assume that we're in lowest terms here when we say it's rational. We can say that it can be written as p over q, where p and q are integers but non-zero, and p over q is in lowest terms. We can assume that too. You can always put something in lowest terms, no problem. Okay, integers without 0. All right, so now let's do some math. Okay, so, or some algebra rather, some manipulating equations. So the first, obvious thing to do is to take this equation, multiply both sides by q. So we get root 2q times q is equal to p. And this implies, if we square both sides, that 2q squared is equal to p squared. And so what does that say? That says that that p squared is even, right? 2 times an integer, so p squared is even, and hence 2 divides p squared. And hence 2 divides p. Okay. And so, all right, so 2 divides p squared implies that 2 divides p. Think about why this is true. Okay, why does 2 dividing p squared imply that 2 divides p? Well, this means that we can write p as 2k, where k is in z without 0. Okay. All right, so this is the first piece of information that we have. And then from here, we can go ahead and do the substitution. We can say, okay, well, since p is an even integer, we can substitute that in right here. And we can say that, therefore, 2q squared is equal to 2k squared, which implies that 2q squared is equal to 4k squared, which implies 2q squared is equal to, q squared is equal to 2k squared. And this implies that 2 divides q squared, which further implies that 2 divides q. Therefore, okay, so what have we just deduced? We've just deduced that that both p and q are even, right? 2 divides p and 2 divides q. Okay, so we've deduced those two things, but that's a contradiction. Okay, why is this a contradiction? And then the sign for contradiction are these two arrows that run into each other. So why is it a contradiction that 2 divides both p and q? Well, up here, we assumed that p and q were in lowest terms. That means they can't have a common divisor that reduces them even more. So this is a contradiction because we assumed that p and q had no common divisors, right? Because they were in lowest terms. And therefore, since we have a contradiction, our original claim that root 2 was rational is false. Okay, so root 2 is irrational. So the next type of proof I want to talk about are these if and only if proofs. And so these are just direct proofs, but we prove the forward direction and the backward direction, kind of like the subset stuff that we were doing to show set equality. We showed both containments. And so that's what we're going to do here. And so the idea here is that if you have a statement, A, if and only if B, you want to show that A implies B, and you also want to show that B implies A. So let me show you what I mean here. So for this example, we want to show that, let me make sure I'm recording here. Yeah. Okay. So for this example, we want to show that A intersect B equals A if and only if A is contained in B. So the stuff before if and only if is our premise A. So this is our A, if and only if, and our B is A is contained in B. Okay. So let's show the forward direction. So we want to first show the forward direction that A intersect B equals A implies that A is contained in B. Okay, so we want to assume this and show that it gives rise to this. Okay, so proof. So we're going to assume that A intersect B equals A. And so off to the side, we can draw a little picture here. What does that mean? Well, the only way that A and B are going to intersect and we're going to get A is if A is completely contained in B, right? We can't have a situation like this because that's not all of A. So what does that look like? So it looks like this. So we have A is contained, A intersect B is just A. So this is A and this is B. So the intersection, the things that are both in A and B are just A. That's the intersection here. Okay, so we want to assume this. And and so if A is in A, then by our assumption, A is going to be in the intersection of A and B, right? A equals A intersect B. And therefore, A will also be in B. Right? If it's in the intersection of A intersect B, it's going to be in B. Okay? Okay. So that was that direction. Good. So that shows that A is contained in B. Now let's show the other direction. So the second direction we're going to show is that A being contained in B is going to imply that A intersect B is equal to A. Okay, so let's show this. So again, we're going to assume the premise here that A is contained in B, and we want to show that it implies A intersect B equals A. So suppose that A is contained in B. What does that mean? Then whenever A is in A, this means that A has to be in B. That's just a definition of being a subset. All right, and we want to show this equality. So remember, to show a set equality, we need to do both containments. So for the first containment, we show that A intersect B is contained in A. Well, that's true just by the definition of A intersect B. That's stuff contained in A and B. So that's true by definition. Not too hard to show that. And then the other containment, so A is contained in the intersection of A and B. So again, we're supposing this guy, suppose that little a is in A. So suppose that little a is in A, and we want to show that it ends up here. Well, by our assumption that we had, so we suppose that A was a subset of B. Whenever A is in capital A, it's also in capital B. Okay, so we use that here. So suppose that little a is in A. Then by our assumption that I've underlined in red, A must be in B as well. So remember what it means to be in both A and B. It means that it's in the intersection of A and B. Thus, little a is in the intersection of A and B, and we are done. Okay, so we have shown if and only if. So again, just to recap the if and only if, you always want to prove both directions. So the thing before if implies the thing after if, and then you want to show the thing after if implies the thing before if. Okay, so that's how you do an if and only if proof with sets. Okay, so let's go ahead and do another example. So this is an if and only if example. We have a function from A to B. We want to show that it's injective if and only if this set equality is true. Okay, so let's start with our first direction, the forward direction, as they say. So the forward direction is what? Well, what comes before the if and only if? That our function is injective. So that's our premise here. So we want to show that if f from A to B is injective, this implies, well, our conclusion that this set equality is true. Okay, so let's go ahead and do that. So we start with our assumption that f is injective. So proof. Suppose f is injective. Then what does that mean? So go back to your definition, right? So whenever f is injective, that means that whenever f of x equals f of y, this means that x has to equal y. So that's what injective means. This is just the definition. Whenever f of x equals f of y, x equals y. All right, and now we want to show that this implies this guy right here. So these are sets, okay? So let me just remind you what this f capital X is and f capital Y is. I'll write this off to the side up here under scratch. So f capital X is a set. And so all it is, it's literally just the set f of x such that little x is in capital X. Okay, so that's a set here, and, analogous definition for f capital Y. So f little y such that little y is in y. That's what these sets mean. All right, so for set equality, we're trying to show both containment. So we want to show first that f capital X intersect y is contained in f x intersect y. So this is the first thing we're going to show. All right. All right, so we want to let something be in here and show that it ends up in here. Okay. So I'm just going to say we're going to let W be in this intersection of sets. Okay, so we're going to let W be in this intersection. And so that means that there exists X in capital X, Y in capital Y, with W equals F little x equals F little y. Okay, so that's just what W being in this set means that it's in both F capital X, so there's some little x for which F of x equals W, and there's some little y for which f of y equals w. Okay, well, what do we have now? Okay, well, our assumption, okay, what we can use here is that f is injective. All right, remember, we're trying to show that injectivity implies equality. And to get to the full equality, we have to show this first containment. So, injectivity says whenever f of x equals f of y, that means that x must equal y. So let's use that here. So here, since f of x equals f of y, so since f of x equals f of y, by injectivity, x must equal y. And therefore, W, well, I can actually just say this. I can say that x and y, since x is in capital X, y is in capital Y, and they equal each other, we can say that little x and little y are in the intersection of capital X and capital Y. All right? And therefore, W, which equals f of x and f of y, must be in the intersection of capital X and capital Y, right? Because little x, little y are in the intersection. And so, yeah, this guy is in here. This guy is in here as well. So, of course, this guy must be in there. So we've proved that first containment. And now we have to show the second one. So the second containment, we're still working on the forward direction that injectivity implies this set equality, but we need to do the other containment, which is f capital X intersect y is contained in f capital X intersect f capital Y. Okay, so let's go ahead and show this. All right, so again, same story. We want to pick something in here and show that it ends up in here by our assumptions. Okay. So let's suppose that Z, I don't know, I'm just using a different letter here. Z is in F intersect capital X, capital Y. Okay, so what does that mean? Well, that means the following. Then Z is equal to F of Y. Oops, not F of Y. Let's do F of W. For some W, little w, in the intersection of capital X and Y. Okay, so that's just what that means. If Z is in the image of this function evaluated at X intersect Y, then it's going to be equal to F of W, where that W is going to be in the intersection of X and Y. Okay, so just using the definitions here. All right, so what does this mean? So this means that F of W is in F of Y and F of capital X. So F of little w is in F of capital Y and capital F of capital X, right? And so that's precisely what we're trying to show. Okay, so if F of little w is in F of capital Y and F of capital X, then it's in the intersection here. And of course it's, it's Z. That's what we assumed here. Okay, so we've shown both of these containments, and so we've shown the forward direction. Okay, so now we need to show the other direction. We need to show that the set equality being true shows that F is injective. Okay, so let's go ahead and look at that. So this other direction, we want to show that so if this, let's actually make this equal. So if this is equal, then this proves that F is injective. So to try this proof, let's try to derive a contradiction here. So remember, the set equality is going to hold for all. Let's go back up to the original problem statement. So this is going to hold for all X and Y contained in A. Okay, so contained in our domain A. And so the idea here is to derive a contradiction by picking capital X and capital Y, so that, we end up with a contradiction. And again, if you're not seeing this at first, don't worry about it. It takes time to get used to these. Okay. So let us suppose that F is not injective. Okay, so we're going to try to derive a contradiction here. Okay, so and the contradiction is going to come from the set equality. We're going to try to show that something goes wrong when we assume that F is non-injective. So what does it mean for F to not be injective? Well, that means that then there exists elements A1, A2, and A such that f of A1 equals f of A2, but A1 is not equal to A2. So that's what it means to not be injective. We have some elements that fail this one-to-one property. Okay? Okay. So here's what we're going to do. Remember that this property should hold for all x, all capital X and capital Y in capital A. So choose, so the idea here is we can choose capital X equal to A1, the set, just the set A1, right? That's a subset of capital A. And capital Y can make subset containing A2. Okay? So by our set equality up here, what does that mean? Well, this means that we should have f x intersect y is going to be the set A1 intersect the set A2. And that should equal f A1 intersect f A2. All right, well, here's the problem. The problem is that A1 and A2 are distinct by the way that we chose them. And so the issue here is that this set intersection of A1 and A2 is going to be empty, okay, since they're distinct elements. So this is going to be f of the empty set, and this should equal the intersection of f A1, A2, which by assumption we said that f of A1 does equal f of A2, so we can just choose this to be f of A1, or if you want f of A2, doesn't matter. But this is non-empty, right? We chose A1 and A2 to be elements such that f of A1 equals f of A2. But the problem here is that whenever we apply a map, a function to the empty set, it's always going to be empty. Okay, so f of the empty set is going to be the empty set, and it's saying that this is equal to f of A1, but f of A1 is not empty by assumption. So this is a contradiction. And therefore, f must be injective. Okay, so we've proved both the forward and the backwards directions, and so we are done with our proof. All right, so now we'll talk about contrapositive proofs. This is another way that you can prove things. Let's see. So instead of just proving a direct implication, A implies B, what we can show instead is that not B, so the opposite of B implies the opposite of A. Okay, so that's logically equivalent to A implies B. All right, so let's try to do this example right here. So we want to show that if A is contained in B, then A intersect B complement is the empty set. So let's do the contrapositive way to do this. So, our B is going to be after then, right? That's our conclusion. So this is our B, and this is our A. And so to show the contrapositive, we want to show, let's just write this off to the side. We want to show not A intersect B complement equals 0 implies not A intersect B. So in other words, A intersect B complement is not the empty set, implies that A is not contained in B. Let's write that out. In other words, A intersect B complement is not empty, implies that A is not contained in B. Okay, so this is what we're trying to show, this right here. This is the contrapositive statement of our original statement. Okay, and it's logically equivalent to A implies B. That's why we can do this. So let's go ahead and show it. So suppose, just start my proof here. So suppose that A intersect the complement of B is not empty. Okay, so what does that mean? Then there exists, so that's what this means. If you haven't seen this before, there exists. I'll be using that for shorthand from here on out. So there exists some element, some X in A intersect B complement. And what does that mean? Then X is in A and X is in the complement of B. And what does it mean to be in the complement of B? This means that X is not in B. Okay? So we have that X is in A, but that implies that X is not in B, and so A is not contained in B. Okay, so that is the idea behind these contrapositive proofs. So the next type of proof we'll look at is proof by induction. And so the idea here is that we show that a rule works for the very first case, and we show that there's like a domino effect. So we assume that the rule is true for the nth case and show that this implies it's true for the n+1 case. So let's look at an example. So our example is we have x sub 1 equals 1, and we have that for each n in the natural numbers, which natural numbers are just the counting numbers, 1, 2, 3, etc. We want to define x sub n plus 1 equals a half times x sub n plus 1. And so the first thing we do in these types of proofs, and let's see, and well, okay, and then we're trying to prove, let me write what we're trying to prove, that would be helpful. We're trying to prove that x sub n is less than or equal to x sub n plus 1. Okay, so for all n, we want to prove this. And so we want to start with the base case for these inductive proofs. So that's the very first possible natural number that we want to show that this inequality holds for. So the base case is when n equals 1. So you want to ask yourself, is it true that x sub 1 is less than x sub 2, right? That's just inserting 1 in for n into this. So is this true? Well, let's see. So by this rule here, we have that x sub n plus 1 is a half times x sub n plus 1. So that means that x sub 2, x sub 1 plus 1, is simply 1/2 times x sub 1 plus 1. I'm just literally putting n equals 1 into this rule. Now x sub 1 was given as 1, and so we have that x sub 2 is equal to a half times 1 plus 1, which is 3/2 or 1.5 if you like that. And that is true. So this is true because x sub 1 was 1 and x sub 2 is 3/2, 1.5. Okay, so that's true for the base case. And now we want to assume the inductive hypothesis and show that when assuming this, it creates a domino effect. And so what do I mean by this? Okay, so the inductive hypothesis. Assume that x sub n is less than or equal to x sub n plus 1, and show that this implies x sub n plus 1 is less than or equal to x sub n plus 2. That's what I mean by the domino effect. So showing that the previous instance implies the next instance is true for the rule. All right, so this is what we're going to assume, and we want to show that this holds. Okay. So assume that x sub n is less than or equal to x sub n plus 1. And so since this is true, if we multiply both sides by a half to introduce this rule up here, let me actually write this off to the side. So this is off to the side. We have x sub n plus 1 is equal to a half times x sub n plus 1. Okay, so if I multiply by a half, I'm getting a half x sub n is less than or equal to a half times x sub n plus 1. And so if I add 1 to both sides, I get a half x sub n plus 1 is less than or equal to a half x sub n plus 1 plus 1. And so by our rule up here, this is just x sub n plus 1, right? This guy right here. And this is going to be less than or equal to, well, again, by our rule, let's see. Let me write this a little bit better. So again, by our rule here in purple, a half times x sub n plus 1 is going to be x sub n plus 2, right? Because if this is plus n plus 1, this thing has to be n plus 2. So this is going to be x sub n plus 2. And so we've shown everything that we need to show. We've shown that the base case was true, so the smallest possible n that we could choose, the rule holds true. And we've showed that if we assume that x sub n is less than or equal to x sub n plus 1, by the base case, since we have that, there's a domino effect, and that implies that x sub n plus 1 is less than or equal to x sub n plus 2. So that is a little review on proof by induction. Now let's look at another proof technique. So something that you'll have to do in homework eventually is to show uniqueness. And so how do you do that? Well, the strategy is that you assume that there are two things that satisfy a given property and show that this means that these two things are equal. Okay, so here's a simple example. Suppose that a is not equal to 0. We want to prove that ax equals b has a unique solution in the real numbers. And so the idea here is to assume that there are two different solutions. So let's see what that implies. So suppose that x1 and x2 are solutions to this equation, to ax equals b. And so then we have the following. We have ax1 equals b, and a times x2 is equal to b. All right, and so if we do some manipulation here, just subtracting b from both sides, we get a sub x1 minus b equals 0, and a sub x2 minus b equals 0. So both things equal 0. We can set them equal to each other. So this implies that a sub x1 minus b equals a sub x2 minus b. And if we, we can cancel out the b's, right? We can just add b to both sides to give us this. A sub x2. We can subtract again to get a times x1 minus x2 equals 0. And so, you learned in college algebra, whenever you learn this, we have the zero product property. So we either have a equals 0 or x1 equals x2. And we assumed that a was not equal to 0. So that means that x1 is equal to x2. And so that's how we can show that the solution is unique by doing something like this. Okay, so I think that was all I wanted to review with the proof stuff. I wanted to talk a little bit about fields. So a field is a non-empty set with two operations, addition and multiplication, that satisfy a bunch of really boring axioms. But the reason I wanted to talk about this is because we're doing real analysis, which, hence the name, we're looking at real valued functions, real valued sequences. So I think it's a good idea to talk a little bit about what the real numbers actually are in terms of its classification as a field. Okay, so these are the really boring axioms that, from taking Algebra 1, Algebra 2, but they don't go into depth and tell you, all of this stuff when you're taking high school algebra. But basically, the first axiom says that if you have two things in a field, they're commutative, so you can switch the order of addition and switch the order of multiplication. You know this, 2 times 3 equals 3 times 2, blah, blah, blah. Distributive laws, same thing, about this from algebra. It's just exactly what you think is happening. Associativity, we can group, when we're adding or multiplying, we can group the numbers in any which way we'd like. The fourth one is that we have what's known as the additive identity in every field and the multiplicative identity in every field. So the additive identity is 0. Whenever you add something in a field to 0, you get that thing back. You know this. 3 plus 0 equals 3. 5 plus 0 equals 5, etc. And every field has a multiplicative identity, which is 1. So you multiply anything by 1 in your field, you get that thing back. We all know this about real numbers. The next thing is inverses. So fields are kind of special because they have multiplicative inverses and additive inverses. So if you ever have a number in your field, you're always going to have the negative of that number. That's called its additive inverse. And one thing that's true about fields that's really nice is that if you have a number in your field, you're always going to have a multiplicative inverse, which means there's something in that field such that when you multiply it by that number, you get 1. So for instance, in the rational numbers, a multiplicative inverse for 2 would be 1/2, right? Because when you multiply 2 and 1/2, you get 1. So this is nice, this multiplicative inverse. And then finally, closure. If you have, and this is going to probably come up a lot in your math career, but closure means that if you have two things in your field, when you add them together, you get something else in your field. If you multiply them together, you get something else in the field. Okay. Honestly, kind of boring, but I did want to talk about this just because we are talking about the real numbers. So here's some examples of fields, okay? And there's way more than this. If you go on further in math, or maybe if you've taken an algebra class, you're going to see a field called z sub p. And so this is just the numbers, the integers modulo p, where p is prime. But I'm not going to get into that here. If you're curious, you can look it up. But yeah, so these are fields, and what you should do is you should verify the boring axioms just to give yourself some practice. Convince yourself that these are fields. So verify that all 3 of these things have these 6 axioms. Not a field. Why not? Well, if you can find one of those axioms that isn't true for these sets, then it can't be a field if just one of them's not true. So think about your natural numbers. Okay, so your natural numbers are 1, 2, 3, blah, blah, blah. I mean, you know, it's, the natural numbers aren't even what's called a ring, because they don't even have their additive inverses included. Like -1 is the additive inverse for 1, that's not included, blah, blah, blah. So we can automatically say this is not a field, no additive inverses, and no multiplicative inverses. Really, like, not a field. Oh my gosh, not a field. Okay, so this one, the integers are not a field either. Because, yeah, we have additive inverses in the integers. The integers are what we call a ring. Maybe we'll talk about rings, but probably not. I don't know. But there are no multiplicative inverses. So other than, 1 has its multiplicative inverse in there, which are called, they're called units, but whatever. Anyway, but not all of them have multiplicative inverses. Like 2. 1/2 is not in this set, okay? So no multiplicative inverses for every element. I mean, there's some for, like 1, the multiplicative inverse for 1 is obviously 1, and that's in there, but in general, for numbers like 2, 3, 4, etc., we don't have multiplicative inverse. So these are not a field. And that's all I want to talk about this week. So thank you guys so much for listening and following along. And I'll see you guys next week for our first analysis lesson.